Welcome to video 9.5b, apply the distance formula. Before I get started, for the distance formula, I prefer this version. Instead of that x sub 2 minus x sub 1 squared, I prefer the distance equals the square root of the change in x squared plus the change in y squared. Because it doesn't really matter if it's negative or positive. When you square it, you get the same result. So it eliminates some of the sign errors. All right, so here's example 1. Show that the points A, B, and C as shown are vertices of an isosceles triangle. So I've taken the liberty of already drawing this figure just because I'm a visual person. All we've got to do now is find the distance between the points, and for it to be isosceles, at least two sides have to be congruent. All right, so I'll find the distance from A to B. Again, if there's no segment bar above it, it means the distance from point A to point B. All right, so that distance will be the square root. I'll call this x sub 2, y sub 2, x sub 1, y sub 1, just for the distance formula. So it'll be 7 minus 5 squared plus 4 minus 2 squared. That will be the square root. Now a minus is a positive, so it's going to be 12 squared plus 2 squared. So it's going to be the square root of 144 and 4. So it's going to be the square root of 148. I don't have to worry about simplifying. I just have to show that they're the same distance. So I'll leave it in that form. Now from A to C. So now I'm going to use this method and just show you how it's a little bit easier. So from A to C, the square root, the change in x from negative 5 to 2, well, that's 7 units. So 7 squared plus the change in y from 2 to negative 3, that's 5 units. So that's going to be the square root of 49 plus 25, which will be the square root of 74. Again, I don't have to simplify, I'm just trying to show that they're the same distance. Now from B to C, again, I'm going to use this formula here. So from B to C, the change in the x values is just 5. So it's going to be 5 squared. Plus the change in the y values, that's going to be 7. So 7 squared. So it's going to be the square root of 25 plus 49, which will be the square root of 74. So now, since these two have the same distance, I know I'm isosceles. So I'll say, since AC is congruent to BC, it's an isosceles triangle. And again, you can't just write that. You've got to show your supporting work. Okay, example 2. Show that the diagonals of rectangle ABCD with these vertices are congruent. Well, we know that the diagonals of all rectangles are congruent. We're just more or less showing it in this example. All right, so I've already drawn the figure. I just have to figure out the distance of AC and the distance of BD and show that they're the same. All right, again, I'm going to use this formula right here. So AC, here's AC. The change in x from 0 to 8 is 8, so 8 squared. The change in y from 0 to 6, that's 6 squared. So that's going to be the square root of 64 plus 36. That's the square root of 100. I'll just figure that out as 10. From B to D, the change in x, again, is 8. The change in y is 6. Once again, I don't care if it's positive 6 or negative 6. When I square it, I get the exact same result. Same thing with positive 8 or negative 8, I don't care. That's why this is so much easier to use. So that's going to be the square root of 64 plus 36 equals the square root of 100 equals 10. So since AC is congruent to BD, the diagonals are congruent. Again, you've got to show your supporting work. So there you have it, a couple examples applying the distance formula, and moreover, my simplified version of the distance formula.